teacher from the San Diego area has come up to present to us a wonderful class on the Arduino Dewey Milli-Lanova versus the Uno and how they work. I turn the floor over to you.
Thanks. Yeah, good to be back. I teach electronics, computer programming, and robotics in San Diego, so I like this stuff. I only get up here about twice a year. Yes, sir.
Where do you teach it at?
I teach at ITT Tech in San Diego. I've been there for almost 17 years. I only get up here a couple times a year because for the last 10 years I teach Saturday morning and Saturday afternoon classes, and I can't hardly ever get out of them. So this year it turns out I'm clear now. I'm clear in June. So whenever I can, I'll get up here. If I ever retire, I'll be up here every month if I can, as long as I can make it. Anyway, I have 6 topics today, and you can go from 1 to 6. It's totally up to you. I'll tell you what's going on, and then I'll let you decide what you're interested in. This first one is going to compare the two boards, Dewey Milli-Lanova, which is Italian for 2009, Uno, which is Italian for 1, because these boards were built by Italians, and of course the Dewey was built in 2009, and that's how it got its name.
Okay, Dewey I can pronounce.
Yeah, Dewey is good. I also have a presentation today on the sharp distance sensors, on the infrared sensors, and how the technology works. A lot of you may know they work. If you don't know how they work, I'll go through that today. And these are just real short things. I don't know if you want to talk about those or see those tonight. I have some photos and some discussion about a clothesline racer competition held in San Diego 2 weeks ago. I also built a timer for that clothesline race using the 7-segment LED shield that goes on to the Arduino board. So I built a timer that works. It's accurate to within 1/100th of a second, and we'll use that in the racers. Also, you guys have been invited to the RSSC competition in June, in which they're going to have a hall following contest. I'd like to talk about that because what I talk about for the sharp sensor is important. If you're going to use infrared sensors, probably the sharp is the way you want to go. If you're going to use acoustic sensors, most of you are going to want to go with perhaps the ping sensor. That's the one you might be the most familiar with. I'm going to show you an alternative to that that's the same price, totally easier, no programming. It's constantly pinging and constantly providing an analog signal to your computer so that you can do range. So I'd like to get a discussion going at the end about if you're going to compete in that contest, which is the best sensor, infrared or sonar, and why. And then and I have enough information, hopefully, to help you if you're on the edge to decide which sensor is better for you. So that's my menu. We'll start with these two, and then we'll see how you want to go from there.
What was the name of that competition?
The RSSC one? They're calling it the hallway competition. It's in June. The way it works, there's a really long hallway in the building. It's in an academic building. In the middle of the hallway is like an alcove that goes into where the elevators are. So for now, let's make this the elevators, and let's make this the long hallway. The contest is you start from a spot, and it's not a spot that the robot can detect, 10 feet from the little alcove. Your robot runs all the way down to the end of the hall. It's probably 100 feet. There's a door down there. You go down to within 2 feet of the door. You turn around. You come back. You go into the alcove with the elevator. You come out of there. You go all the way down to the end of the hall. Then you come back. When you get back to the alcove, the idea is to get as close to that spot that's 10 feet past the elevator as you can. And the spot is so tiny that the robot can't detect it. The whole idea is you either have to detect the elevator area or detect that wall and then go 10 more feet and boom, and the dot will not necessarily be in the center of the floor. So it's a hallway and the dot could be off to the left or off to the right. So once you know where the dot is, you can do whatever you want to decide to get your robot there. So, yeah, it's all autonomous. You can't control your robot. It works with that. So the idea is you turn your robot loose and it comes back to that spot. So obviously, to finish is to win, but they're also saying whoever's the closest to the dot is number one. So I'd love to talk to you about the technology of how to beat that particular contest with the sensors that you have available to you. So we can talk about that if you want.
Are we invited to compete in that competition?
You can,
Or are we
anybody,
invited to watch?
you,
Oh, it's a competition where everybody's invited to compete.
Oh, okay.
if you want, you can join their club online. It's a Yahoo club. It's like instant joining, but they don't limit it. And Bill has a robot that looked impressive last
Yeah,
week.
I did the loop and came within 12 inches of my start line.
So we have,
Did ya? All right, that's a good start. You can't get a whole lot closer than that.
we have some competition with Bill. Okay.
So I'm going to talk specifically today about two of the boards that Arduino makes. Now, here's kind of the entire menu of the stuff they have. Maybe you can't even read this. I don't care. You don't have to read it. But essentially, there's the Gia Simila. Okay, that's obsolete. It's been gone for years. You don't have to worry about it. The two older versions are the Due Millenove, which is now obsolete. It's been replaced by the Uno. And the Mega board, the Mega chip, which is now obsolete, it's been replaced by the Mega 2560. So, if to understand the family of those chips, I just want to give you a little bit on the specs. I want you to notice that the memories in kilobytes are all incredibly small, 16.5, 1632. Notice that when you get to the Mega, all of a sudden memories jump up. You start getting a significant amount of memory, or an amount of memory that you can use for larger projects. As far as digital I/O pins, all of the smaller boards have 14 digital I/O pins. And of course, the big guy, the Mega, has 54. So once you've exceeded this 14 I/O pin limit, you've pretty much got to go to the Mega. Pulse width modulation. I don't know how much you guys know about pulse width modulation. You think of these boards as having analog pins, or analog input, or analog output. Sure enough, there's 6 analog pins, or 16, on these two boards. They're really not analog. They are not true analog. Now, for those of you that don't understand that, just take my word for it for now. For those that understand the electronics of it, let me explain what happens. The analog input signal is between 0 and 5 volts. The Arduino board has a built-in 10-bit A to D converter. And I think you know 10-bit. A byte has 8 bits, and there's 8 ones and zeros. That gives you 256 combinations. Who knows how many if we go to 9 bits and 10 bits? 9 bits.
1024.
1024, because the 256 with one more bit doubles, with another bit doubles again, so 256 times 4 is 1024. So 0 to 5 volts, if I cut it down to a binary number with 10 bits, I can do everything from 10 zeros, which is 0, to 10 ones, which is 1023. I now have 1024 possibilities. So this analog input into the pin is converted to a digital binary number between 0 and 1024. Y'all see that? So the inside of the chip doesn't know 3.6 volts. It knows 642, or some number between 0 and 1024. So as long as you understand that, you know that there's no true analog in this chip. That'll help you understand what's going on. But anyway, there are at least 16 pins. Now, you think of these as analog pins, they're also digital pins. Every pin on the Arduino boards can be used for digital, every single one. For digital in or digital out. So, in that sense, don't worry about it. You've got a lot more digital inputs and outputs. Now, when I first made this presentation a couple of years ago, the Due Millenove was the only board or chip on it. And of course, the Uno came out, and the first question became, you know, what's the difference? So of course, the first thing I did for my students is I ran out and bought 10 Unos, and then I had to figure out the difference. So since I have 10 or 15 Unos, and I got 10 or 15 Dues, and my students kind of just grab one and use it, I do want to tell them at some point what's the difference and how they work. Okay? Digital pins, they both have 14 pins. What I want you to notice in this is that almost everything's the same. There's very little difference between these two boards. You can look at them as being totally interchangeable. They're pin compatible, same with almost everything. So 14 digital pins, meaning that they can either be set up as input pins or output pins. You either output 0 volts or 5 volts, or you can input something close to 0 volts or 5 volts. So those are your digital pins. They also have other uses, which I'll get into shortly. The current limit on each of these pins is 40 milliamps. Now, some of you know that a typical LED runs at about what? What's a typical LED run at? 10 milliamps, 20 milliamps. Most LEDs that you see run in the 10 to 20 milliamp range. Okay, most of them will burn out or not last very long if you push them beyond 20. Okay, most LEDs, if you do less than 10 milliamps, you can't see them. They start getting really dim. So when you look at this 40 milliamps, you say, okay, I can run an LED off of this pin. Well, can I run a motor? Well, no. Well, even these little teeny DC motors, these little 5-volt motors pull a quarter of an amp, right? 100 millis, 200 millis, in that range. And of course, when you get any kind of size of motor, you start getting up into half an amp or an amp fairly quickly. Okay? So the real rule is you cannot run any of these high-powered devices. Relays. Relays have a coil that takes a lot of current. Okay? You can't run high current devices off these pins, but you can run LEDs. You can send the 5 volts out of these pins to a transistor, to the base of a transistor, and then if that transistor can handle 2 or 3 amps, then it can turn that 2 or 3 amp source on or off, but it can't run 2 or 3 amps itself. You can use it to drive higher amperage circuits. At any rate, 40 milliamps is the limit for each pin, and there's a 200 total for the entire board. So if you need high power, then you need to do something different. There are 6 analog pins, and again, as I've said, they're not true analog, but they work. The only difference really is on the new board, they're labeled as A0, A1, A2, and you call them that in the code. You set up the pin letter as A0 or A1 or A2, and the machine and the programming language understand that. Now I talk again about analog. On the old board, the letters PWM are next to 6 of these pins. On the new board, there's a little squiggly. Well, the little squiggly looks kind of like a sine wave. On your typewriter keyboard, it's the tilde. That very top left character on your keyboard is called the tilde. The tilde is often used to represent AC because it's actually a little sine wave. Okay, it's really a proofreader's mark. It's not really an electronic symbol. But anyway, so the PWM and the tilde, or the squiggly, both mean that this pin is capable of putting out pulse width modulation. And that's a whole separate lecture on itself, which I'll get to at some point, maybe someday up here if you want. The power for this is pretty nice. It's pretty clever. You can power this up one of 2 ways. You can use the USB port, and of course you have to use the USB port to program this puppy. Okay, that's the main way to power it up when you're programming, when you're working on it. But you can also use the standard 9-volt adapter pin to plug into the power connector. It is a smart power supply. It does look at which one is there, and it picks the one that's the best. So you can hook it up either way. So if your project requires that it's always near the computer and it's always right there, then you can just continue to use the USB to power the board. If your project is a robot and it's got to run around on the floor and it can't be connected to something, then obviously you want to put a 9-volt battery on board and run it from there. Speaking of 9 volts, 7 to 12, that's the magic number. Do not power any of these boards with less than 7 or more than 12. Less than 7, what happens is you don't get enough voltage through the voltage regulator, and weird things start to happen. 1s turn into 0s, and 0s turn into 1s, and it's pretty much unpredictable. You're basically running the board down into the lower limits where it doesn't know what to do. Can't figure it out. So stay in the 7 to 12 volt range, meaning that 9 volts is pretty much your best bet. There's a pin on the board that just says 5 volts. Well, inside the board, you put into the board, in fact, you can actually use this VN pin. Also, that's a third way to power the board. You can use the VN pin, run your 9 volts in there. But once that VN comes in, it goes to a 5 volt regulator. It regulates 5 volts for the entire board. So these 5 volt pins are just coming off of the 5 volt regulator. So if you have something else that's 5 volts, maybe you have some external AND gates, OR gates, an H-bridge driver, or something that you need 5 volts for, that's where you get your power supply for your external 5 volts. There's also 3.3 volts. On the older chip, there was something called the FTDI chip. FTDI is a proprietary, it's a company. They built the thing that teaches this machine how to speak serially to the PC. Arduino dumped it because it was relatively expensive, it was proprietary, they wouldn't give them a discount, and they basically said, no, we want something that's open source, we want something that we don't have to pay so much money for. And you'll see on the new board that this chip is now gone. That's probably the major difference. However, that chip is, some of you know that some chips, now some of the newer chips, newer meaning, I don't know, 20 years ago, whenever they came out, newer chips started running on lower voltages. There are 3.3 volt chips out there and 3.3 volt devices out there. Since this FTDI chip was a 3.3 volt device, they put it on the board and they've kept it there. So all that pin does, it allows you to tap off 3.3 volts in case you have a device that needs that as its main voltage. And of course there's ground pins, they're all the same, there's 3 of them. They're just located in different places to make it handier for you, the designer, so any external circuit that you want to hook up the ground has got to be done that way. So they're pretty obvious. Now we're talking about some of these pins that have dual uses. When you're hooked up to the board through the USB port here, and you tell your board to speak serially to your PC, that serial signal comes through the USB to the PC. That's how you communicate with the PC, through that USB cable. But what if you want your Arduino board to communicate serially with some other device? Some kind of a temperature sensor or a monitor or some signal from somewhere else. You want it to be able to talk serially to some other device. Well, that's what pins 0 and 1 are. 0 and 1, notice it says TX, RX. TX is short for transmit, RX is short for receive. In serial communications, it's typically a 2-wire circuit, a transmit wire and a receive wire. So if you're going to use serial communications with another device on your robot, on your machine, whatever it is you're building, those are the 2 pins you can use. What that means, of course, if you're going to speak serially to another local device, you can't use digital pins 0 and 1. Other uses. Some of you know what interrupts are. Basically, a computer has many devices vying for its attention and for its time. Your computer has a mouse, a keyboard, a touch screen, whatever your computer has, it has a number of input devices. Your hard drive, it's an input device. There are a number of, your modem, it's an input device in the sense that all of these ask the computer to do things. Well, the way an interrupt works is it says, look, I know you're busy. I know you're running this program. I know you're doing your job. But I need service. I need something to happen. So the way that PCs, and they were the first machines that did this big time, and it pretty much caught on, did was says, look, the computer's just going to run its program, do whatever it's doing, and wait for somebody to interrupt. Now by somebody, I mean the mouse, the keyboard, a disk drive, a modem, something, the USB cable, all of those things have to go to the PC and say, look, stop what you're doing for a minute, I got a job. The human just clicked the mouse. We need to take care of that. Because meanwhile, the computer might be there running a game and saying, okay, what's next? And we're waiting for you to shoot the gun or whatever. In the robots that I built, I typically use one of these interrupts for the robot hit the wall, okay? If the robot hits the wall and you're on carpet and the motor's turning and it's not getting anywhere and it's not pushing, that causes high current in that motor. You don't want that condition to keep going on. That needs an interrupt. It says, I don't care what you're doing, computer, stop what you're doing and handle me. So that's pretty much what an interrupt does. In your PC, all of the interrupts that are human related, the mouse and the keyboard, those all have a very high priority on the interrupt scale. The PC interrupt scale of priorities is the start switch is number 1, on, off. Control Alt Delete is next. And then comes in line all these little guys, the mouse and the keyboard. Anything that's human operated is high on the list. Non-human operated things, disk drives, those are all low on that priority list. So all of these guys can interrupt. Well, microcontrollers in the old days had no interrupt system. And so they started putting it in. So the way this works, you can use pin 2 or 3, or both. In other words, they're 2 separate interrupt signals. You can tell the machine, sit there and listen for a low. When it goes high, call that an interrupt. Or sit there and listen to the high, and when it goes low, call that an interrupt. In other words, you can program this to be either a when it goes high, it's an interrupt, or a when it goes low, it's an interrupt digital signal. So if you need something that needs to interrupt and stop the machine, these are the pins you'll use. Pulse width modulation, I kind of talked about that already. You got 6 pins that you can do that with. On the Arduino series of boards, pin 13 always has an LED hooked up and hardwired. By that I mean right next to pin 13, there's a little teeny thing. It doesn't look like an LED if you haven't seen these little devices. It's a little teeny LED. It says L. It's an LED. It's automatically hooked up. The resistor is already in the circuit. So whenever you send a high to 13, no matter what you're doing with it, that LED lights up. Whenever you send a low to 13, that LED turns off. So it's a good way to test your board. If you want to test your board right out of the box, write a program that says, send pin 13 high, wait 500 milliseconds, send 50 or 13 low, wait 500 milliseconds, and put that in loop in your program, and you can tell your program works. You can tell the program is loaded, you watch the LED blink on and off, and you say, got it. It worked, it loaded, it compiled, it got on board, and it's working. So that should pretty much be your test program for this board. It also has the correct pull-up. How many people know what a pull-up resistor is very specifically? Very specifically. I see 2 hands. Okay, I can talk about that later if you want to. Sometimes you need an outside reference signal, and the one that I use that's the most common that everybody understands is the temperature in this room. In the thermostat system in this room, there's a sensor that says, what is the temperature in this room? Well, that information is worthless unless I know what I want my temperature to be. I don't care what the temperature in this room is. What I really want to know, is it too high or is it too low? Well, I need a reference voltage. I need something that tells me what is the temperature that I want. So anywhere where you need a reference signal from some outside source to say, here's what I want to work around, and that reference signal can change, of course. You can use this as your reference signal. You can then, in your programming, compare what your sensor is reading to the reference signal, and of course ask the true-false question. If it's too high, well, I'm going to do this. If the temperature's too high, I'll turn on the cooler. If the temperature's too low, I'll turn on the heater. the temperature's real close to just right, then I'll leave it alone. So the reference pin or the AREF pin is used for that kind of a deal. The reset pin on the board is just what it says it is. It will totally reset the pin. Now there is a reset button on the board, here and here, and if you want to restart your program, you just tap the button and it'll restart it. But what if your board is inside a robot, inside an airplane, and you want to reset it? You know, you have to have the ability to reset it. So you can actually have the program or even an external device send a 0 to the reset pin, and the board will entirely reset. It'll clear. It's just like Control-Alt-Delete, and the board will reset, set up, and then start running all over again. So you have the ability to reset the board at any time. Shields I'm not going to talk about today. Most of you that are familiar with Arduino know that we have lots of different shields. You'll notice on the Arduino board that there's a string of black connectors on the top on either side. All a shield is some other board that plugs in. You'll see the plugs on the bottom. The plugs on the bottom plug into the plugs on the top. And there's a few boards here today, so I'm sure you guys have seen that and you understand that. So there's tons of different shields that are out there. That's another thing that makes the whole Arduino series really popular, because you have the ability to plug in almost anything that you want. Yes, please. That would be great. Okay. Anyone, just a second. The IDE for this is really easy. I'm not going to talk about this today, but I teach a whole course and a whole class or two just on beginning Arduino programming, and would love to talk about that later. The installation's real easy. Go to the website, download it. There's really only two things you have to do. Once you get your Arduino software running, you have to know what COM port it's on. So you go into Windows, into My Computer Hardware, find out what port just woke up, and use that port. And then, of course, in the IDE, you need to go tell it which board you're actually using. It needs to know that. So that's pretty much the comparison of the two boards and what individually what they do and what they know how to do. Yes, sir?
I just